to one thing and start recording this. Okay. So open up my slides. Here we go. All right, so the lecture today, I want to talk about a very, very important concept of what are NURBS versus MESHES. So does anybody here, can you guys maybe, I mean, you've heard both terms, but does anybody want to attempt you know, early, like a definition of what each of these is? You can say one of them or both of them.
Can I try, Professor?
Yeah.
So from what I know, NURBS are pretty much surfaces or geometries that are composed by mathematical equations, as opposed to vertices, which is, I mean, meshes, which is composed of vertices and different points. I mean, it could be a triangle as expand more up to like a hexagon or even a 7-shaped geometry. So a mesh could be read simpler than a NURB because it's less calculated. Kinda.
yeah. I mean, it's not wrong. Yeah, that's a good working definition. Anybody else has ideas?
Well, I think the meshes are geometry based, while NURBS are more point based. No, I don't know.
I mean, they're both geometry, right? I don't know if you could say one is more, or how do you differentiate point versus geometry? I mean, point is also geometry.
Well, NURBS is like a series of coordinates that relays to each other to create a geometry. When a mesh is a series of triangles and small planes to create the overall geometry.
So there's a difference in the geometric system, right? But they're both geometries, but there's a feeling that one of them is more, you said points linear, the other one is more connected. Is that
yeah.
something you guys agree on?
Yeah. So it's polygonal, while the other one is point based, I think.
Okay. I mean, yeah. We'll let's keep that in mind, and we'll go through a lecture, and then maybe you'll have more specific ideas. Anybody else? Quick? No? Okay. Cool. So I'll start a little bit like with the history and sort of about each of these two systems, and I'll start with NURBS because they go back a little bit further than meshes in terms of where they come from and how they were invented and what they were used for. So you know, in like a lot of technologies that we use today, NURBS were actually invented for warfare. So kind of for the purposes of let's say militant purpose, because essentially here you see the SAGE air defense system, which basically its main job was to calculate something like a flight path. So here you see actually the flight path of an airplane, and they were essentially trying to calculate at what angle do they have to shoot to take down the airplane. So you know that obviously is like requires gigantic calculations, which are really hard to do by hand. And so this was, you know, sort of like an early use of computers that you know, NURBS became really useful for. And here you see, even before the sketchpad, even before the system that I described earlier, you see some kind of like early graphical user interface. And so the questions would be like, why, you know, are we thinking that, why are NURBS the right mode for, why are NURBS the right mode to describe such large surfaces? And the answer is because they're scaleless. So if you think of pixels versus vectors, you know, meshes are kind of like, meshes are, so Illustrator versus Photoshop. So NURBS are kind of like Illustrator, where you can zoom in infinitely onto an image. Meshes are more kind of like pixels, where if you zoom in closely, you will start seeing that the resolution isn't as high. So that's a really, really fundamental difference between the two. And so NURBS were kind of like mathematical descriptions that were describing things at a very large scale, because they were just describing relationships between these different systems. So here, you know, I just mentioned Evan Sutherland and his graphical user interface, and this is some more images of that. So what I find fascinating about these early histories is that essentially, you know, he was already using a pen, so he wasn't, you know, in a way it's almost like we went backwards afterwards with like working with the mouse to actually design something. So the pen is actually a much more intuitive way of designing something. And also here, you know, he talks about the infinite plane that allows you to draw at any scale, that allows you to go in really close. And if you think about it, that just wasn't possible. Everything was in full scale. Everything was in real scale before. Alan Kay is, you know, again, sort of a pioneer of, let's say, graphic user interface, or sort of like thinking about how to, more like generally about like how we're working with computers and how computers can become a creative force. And all these guys were like working at MIT, you know, around the 60s and 70s. Well, you know, actually Gordon told me that he was at MIT at the time and remembers it. So I think it's like kind of like, it's been interesting because it's like a very historical time for me, but you know, there's people around who still kind of are living history in that sense. And so Nicolas Negroponte was another person, you know, that another name that you should hear in that context. He wrote this beautiful book. If you can lend it from the library or have access to it, it's also online. You can leaf through it. Soft Architecture Machines, I really recommend. He was basically really talking about cybernetics and sort of early ideas of how, you know, essentially computer graphic systems would help us to define new futures, or how we can do things like mapping and architecture and so on in a very large scale. So all these people were sort of like, you know, not just on a technical level, but also on a kind of theoretical, philosophical level, kind of thinking about how these new graphical user interface systems can affect architecture. So more specifically, you know, in terms of the software that we are using, you know, that there was sort of kind of a parallel development for a long time, where, or not parallel, but like original development of, you know, purpose of war, purpose of sort of like speculation, but like specifically where NURBS entered architecture was through AutoCAD. And here's a timeline of different software when they kind of were first invented, and when we see AutoCAD is the first one, you know, 1982 is really when AutoCAD was founded, and every other software that you're using in a way is newer than that, which also, you know, you can tell kind of like AutoCAD doesn't feel necessarily new. I mean, it's been upgraded a million times, but it kind of is the grandfather of software. And so here, you know, in the beginning, they had to even explain people. And so AutoCAD, importantly, is a NURBS-based software. So it works with these ideas of infinity. It works with these ideas of, you know, essentially that you can zoom onto something infinitely. And here you see, you know, I feel like often with software, kind of think of it as this like neutral tool, but actually there were very specific ideas behind it. So, and in the case of software, some of the people who were using it, or who were designing it originally, were also architects, and sort of had architecture in mind, even though not exclusively. It was also, you know, from the beginning kind of for other industries as well. And so here you see some early examples of like very early drawings that were made, and here an advertisement of, you know, trying to convince architects to buy this, because maybe it wasn't even that clear to people why they would even need to invest. And imagine $2,000 at the time was like incredibly expensive, so they had to really sell that. So, you know, here you see, you know, how large scale drawings were made before. AutoCAD. So thinking about it, you know, when everything was in real scale, you have to to make something very, very large, you have to essentially sometimes create physically incredibly large drawings, which now we don't need anymore. So this idea of scaling in and out infinitely requires the technology of vectors or NURBS. And Rhino, which we're using today, actually came out much later. So here we are, you know, in the early 80s with AutoCAD, and then late 90s is actually when Rhino emerged. Does anybody, I mean, has anybody kind of heard, or do you guys know how Rhino kind of happened? Since it's the software you're using every day. No? Okay.
No.
Okay. So the way it
I
was.
just assumed it was somebody from Autodesk that left the company.
Pretty much, that's actually correct. So, well, didn't leave the company. It was more that Bob McNeil, which I'm sure you've got many emails from Bob McNeil, but he essentially was an AutoCAD reseller, but he wasn't just selling to architects. He was actually selling to boat manufacturers, and boat manufacturers needed curves because they were not, you know, before most of AutoCAD was essentially just copying and arraying things, and everything was based on the grid. So that's also, I mean, you could argue that a lot of architecture is the way it is because people have been using AutoCAD to draw it, and the easiest command to do in AutoCAD is copy and array. I mean, there's, you know, bigger reasons than that, but it's definitely already embedded in the software that whatever you're designing should be orthographic and should be something that is in a sense repetitive because it's so much easier to draw. So anyway, Bob McNeil, you know, late 90s was realized that there's a need for his ship manufacturer clients to create a plugin for AutoCAD which would be able to draw these kind of complex shapes. But what happened was that you know, it was too complicated to build it as a plugin, so instead he created a new software from scratch, and that is now Rhino. And the new software was specifically meant to be used by AutoCAD users, and that's why Rhino still looks a lot like AutoCAD. So, you know, it's not a coincidence that there's a menu bar that essentially all the general layout is actually very similar, because the idea is that people who learn AutoCAD can easily pick up Rhino as well. And you know, the mathematical formulas that he was using are also actually inspired by the shipbuilding industry. So you guys have, you know, all seen the word spline in Rhino. So does anybody know what a spline is, or can sort of deduct from the images here?
I always thought it just stood for a special line.
So
I always thought it was just like a curve, but there's those points, those like anchor points, like in Illustrator almost.
yeah, exactly.
Yeah, they're interpolated coordinates that are connected by a line.
Exactly, but the mathematical definition for that comes actually from a wooden stick that was also called a spline. So the physical object was called a spline. It was this like soft wooden piece. And here you see an image of it. And then what you call control points actually was called a duck. So these were just little like metal or sort of wooden pieces that you would put in place in order to keep the spline in the right curvature. And because it's wood, it actually has like a natural bend to it, right? And so, you know, the curvature of the spline depends on, you know, how thick that piece of wood is. And so anyway, the mathematical definition actually comes with something in the physical world that is also has the same name. Obviously, we're not calling the control points ducks, but these were like the physical sort of equivalents of what we're now using. Here you see, you know, drawing like an airplane, how complicated that was. They're also calling it lofting, which is funny, you know, coarse and airplane lofting, which is another term that we're using now in 3D. So, you know, the origin in this case is a physical act. The translation is, you know, a mathematical description. Technology now, we use it's a spline with control points or NURBS. And there is certain operations that Rhino privileges. The way that I was saying AutoCAD privileges copy and array, Rhino actually privileges filleting, lofting, and also operations like Boolean and slicing. And so actually throughout you know, researching this, I realized that you can tell if a building has been designed in Rhino. And so, I started researching that, and here those are all confirmed, actually designed in Rhino. So I either knew somebody who was working at the office or had evidence that they had actually worked in Rhino. So this is probably most of you know this on the Highline, a building by Neil Denari. Neil Denari is a heavy Rhino user, and you can tell that these things are filleted, that they're basically splines that have been cut out of a surface and just extruded. And the same thing with the windows. And here, this is a classic loft project by Hedderwick, where, I think it's quite unlikely that somebody would come up with that shape by bending metal rods. Like, there's something very Rhino to me about this, or very sort of spliney in terms of this translation. And here, another fillet project, which also, when Rhino kind of first came out and the software first came out, I think a lot of projects, like especially here, like early 2000s to mid 2000s, like 2000, I would say 2005, 2015 roughly, is like really like kind of like a Rhino era where a lot of people were working in that. And here's some more projects that are also designed in Rhino. And here, even here, you can tell that the pattern was applied to the surface through the Rhino command. Project curve to surface. I don't know if you guys have used it, but it's actually really nice because it allows you kind of like project a pattern to a surface, but it's still, once you know that, it becomes really recognizable.
I always wondered, like, once they have that pattern, it's so specific, and you already have the file for it. Like, I wonder if they send it to a fabricator who laser cuts out of a sheet, like just straight from the model.
Well, fabrication is a bit of a different. I mean, Rhino is often, sometimes it's a design tool. In this case, I'm not entirely sure how the exact process went from like Rhino model to this being fabricated, because those are very large metal sheets. But very often, I've definitely sent laser files straight from Rhino. So I would like generate the file in Rhino. So the way that I would assume this was made, it was probably like drawn on a flat plane. It was projected as a curve to surface to that long curved surface, and then essentially, until the design worked, and then it was projected back onto a flat surface, cut up into pieces so that it becomes like the right size for whatever machine they had, and then it was cut and put in place. But don't take my word for that. I mean, that's like, that's essentially how you could make it, or how you would build a model of that too. Any questions so far, or thoughts? All right, we can move on to meshes, and then we can continue maybe discussion about this. But so meshes, as some of you have said, there's something connected about them. So, in a way, NURBS can often exist in a way almost like on their own, like a point or a line, but meshes, the way you see them always is sort of like they often are there to describe like a kind of shape. And this is actually very important, and in a way very correct, because meshes have essentially been designed to describe reality. And this is the biggest difference to NURBS, which were designed to create reality, right? They were like a design tool from the very beginning. They were always, even the physical form, they were meant to like describe something that doesn't exist yet. Meshes were actually designed to describe something that already exists. So in this case, here you see the, if you think of Sketchpad, they were from the beginning designing houses or designing something, looking towards the future. Here you have, horse or rocket or like whatever description of reality. And so this guy, Baumgart, a little bit later, maybe like 10, 15 years after Eben Sutherland worked on a Sketchpad, he wrote this paper, Geometric Modeling for Computer Vision, where essentially, he was describing the winged edge polyhedron at Stanford, and sort of kind of described it as like something, a proper starting point for building a physical world representation. And so here you have, I love reading like old papers on the internet. You can find that on the internet, and here you can see that already here. Oh, I forgot which parts I wanted to highlight here. I think, oh yeah, I think here, oh yeah. So this is hard to read, but here it's the code, the proper starting point for building such physical world representation. So what I've just read. And interesting for our class also, he used the word photometric data. So we are actually engaged in the representation of the world, and just like he was outlining here, what you need to create a physical representation, you need topological data, you need geometric data, photometric data, so textures. And I'm not sure exactly what he means with part 3 data, but essentially, he was kind of like the first person to kind of like outline in detail how with polygons you can describe reality. And of course, immediately it was used for games like every Graydon mentioned. So here you see him winning the 5-man free-for-all at the first Intergalactic Space War Olympics, where he won the game. So as you can see, like a young guy who was just like developing these ideas at the time. And these are images from his paper. So he already defined the terms that we're using today: vertex, edge, face, and so on. And even these systems that we have a camera, a kind of viewpoint, and we're looking at something. And even here, we're never scaleless. We're not working on an infinite plane. We actually, from the beginning, have to set up a camera. We're not just sort of like zooming in and out of an infinite piece of paper, but we're sort of like setting up a real world scene in real world scale and trying to recreate that. Here's some other pioneers. I'm going to skip over that a little bit, but like those are. Yeah.
I'm sorry. Can you put the name of the article or the book that you just showed us? That one, yeah, on the chat.
Yeah, I can send you that that paper.
Please, though. Thank you.
It's a pretty fascinating read. This is not in the paper. This is just my own research.
Why do you think the paper has so many different fonts on it?
Oh, actually, yeah, it looks really crazy. I think it's just because it's old and probably has been scanned and I don't know, that's kind of how it appears on.
Yeah, maybe it was like corrected.
That's the version that I found, but yeah, I don't know. It looks kind of it's like hard to read.
I think it makes it look even cooler.
Yeah, it looks like a really vintage, right? Even though it's like only, I guess, 50 years old. Yeah, I'll see if I can find like a nicer version. Ed Zayas became famous because he was the first person to actually create a physical, so an animation that represented physics. So sort of in this case, essentially like a volume orbiting around another volume, and that was actually really early in the 60s already. And William Fetter, another sort of veteran who simulated these sort of figures in a flight cockpit. And here just a slide, an example of how from the very beginning, this one maybe applies to both NURBS and MESHES, but like how these technologies were used in art from the very beginning. So cybernetic serendipity is like an art show from, I think it was very early on, like the 60s or 70s, where basically artists were looking at, these emerging technologies and trying to make sense of it and trying to create out of it. Just like experimented in art and technology, which was actually in New York, in the Armory show, and people were essentially taking all these wild new ideas and appropriating them in the works. Here you see again this sort of relationship to original, to the physical world. So again, NURBS describing something organic that is very hard to describe. Imagine trying to model a hand with NURBS. It would be very, very difficult. So MESHES are a much, much better tool for that. And here you can see, literally sort of sketching over a hand and then recreating that hand in virtual space, and the same thing with MESHES. And this was also, Ed Catmull was, I think in the early 80s. So just to go over some basics of how MESHES work. I mean, you guys already mentioned I think you mentioned vertices, edges, and or no, actually, you talked more about NURBS in terms of that. But anyway, the basic unit is the vertex, as you all know. I think the one thing, you never want to call it point. You just always want to call it vertex, just because you want to, you know, you're an architecture student, so you know that kind of stuff. And then, you know, the lines are not lines, they're edges, and then faces are sort of like the solid, full faces. And there's you know, a lot of different kind of meshes, but the most important one are triangular meshes, because triangles can be fit together in any way you want, and that creates a really infinite number of shapes. So basically any shape can be described through a triangular mesh. So it's really popular in architecture, you know, to create essentially organic shapes and so on. The quadrilateral mesh is a little more complicated because it sort of doesn't allow as much flexibility, because basically, so the main thing is you can combine it anyway, and actually the surface will always stay flat, right? That's a huge advantage because you don't have to bend the surface. But here, for example, if you look at this image, you know, if you have 4 edges already, like this square wouldn't actually be a flat surface, which could become a problem when you're building something. So there's only certain types of geometries or ways of these quads coming together that can actually be used in architecture. So here, a beautiful example by Bruno Taut, the glass pavilion, which doesn't exist anymore, but was, you know, an early quad mesh project. And then hexagonal meshes, also, you know, they actually are kind of more like the triangles. They can be combined in any way. So every edge fits to every edge, and in a way allow for lots and lots of different possibilities, but are also, at least when you want them to be actually flat, kind of limited in terms of the shapes you can create. But here, you know, there have been some large scale structures that have been built with hexagonal meshes. One important thing about mesh connectivity, so you can have the same mesh connectivity but not the same shape, because the mesh connectivity just describes how one vertex relates to another vertex and how one edge relates to another edge. So, you know, this vertex relates to this vertex the same way that this vertex relates to this vertex, and this face is exactly, you know, neighboring 2 faces, just like this face neighbors 2 faces, and so on. So actually you can have different shapes but the same connectivity, or you can even have the same shape but like a different connectivity because it's described in a different way. Mesh decimation, I mean, that's something you guys are experts at now, is you know, mesh reduction or optimization is essentially often we need, it really depends on the use, like sometimes you want really high resolution meshes, but often actually the great quality of meshes that they can be reduced and still kind of quite accurately represent what they're trying to show, especially in combination with textures. And then not to be confused with mesh refinement. So mesh refinement actually doesn't change the shape of the mesh, just adds additional polygons. So the mesh would look exactly the same if you don't actually see the wireframe. You just add more to it. And finally, subdivision surfaces. So when you are working, those of you who know 3D Max, you know, very often you start, and those of you who want to learn it, very often you start with a very simple shape like the polygon, and then you start adding more detail from that polygon, from that box. And the way to then achieve like a smooth shape is through subdivision surfaces. So essentially, you put, you know, you apply an algorithm to it, and that algorithm smooths out your shape in a certain way. So here you have the box. Here it's sort of like just one level of smoothness. So it only kind of adds essentially 1 extra square for each square here, and so on. So you can achieve very, very smooth shapes, but it's a very efficient way of calculating this because the computer essentially only needs to understand the initial cube, and everything on top is sort of like parametric, so you can like keep changing it. And for that, you know, there's actually different formulas or different ways of describing that mesh optimization. So with different actual visual outcomes. So you could say that, you know, some of these algorithms in a way have had big authorship in architecture because a lot of architecture has been, one can say, influenced by these, because again, it's a bit like, you know, when I talked about AutoCAD, it kind of has the repetition baked in. Rhino has the lofting baked in. And if you're working with meshes in, let's say 3D Max, or also in Mudbox, actually, if you guys have tried to like increase mesh density command, then it does the same thing. I mean, if you're doing it at a very high resolution, it won't change the object dramatically. But if you're doing it at kind of lower resolution, like from here to here, from here to here, it will actually can change the aesthetic and the shape of the object quite a lot. So here you see, this has the same base polygon, but it has 2 different algorithms applied. So you see how actually the shape is actually quite different. It seems like here the edges have more pull, or kind of like create kind of like a stronger shape, versus here, so like creates a more rounded shape. So I mean, nobody, or very few people today are writing these algorithms themselves. They were kind of like taking those like existing algorithms and working within them, and you can still very much shape them to however you want them to be. But there is definitely some kind of like software bias implicit in using these preset algorithms. So back to our timeline, right? So so remember, Autodesk is like early 80s. Photoshop is also vintage. And actually, so this is for Maya, but actually 3D Max has a very similar timeline. So they're in that sense a little bit interchangeable. So Rhino and 3D Max or Maya originate from around the same time. Kind of similar to Rhino had like a prehistory with AutoCAD. Maya also had a prehistory with Alias, and then also Wavefront. But in its current format, it's also kind of from the late 90s. And so just like I was describing in Baumgart's essay, if you think of 3D Max, it always has kind of the physical camera, the physical scale is very present. It's almost like shooting a movie, and it's also being used for movies. That's kind of like its origin. So here Ed Catmull is, the guy who essentially developed one of the main algorithms, subdivision algorithms, and he also worked on Toy Story. So those people are sort of like often working in animation industries, but then influencing architecture as well. Bill Kovac is one of these interesting figures. So he was actually an architect working at OMA. This is a picture of him. Oh, sorry, it was not OMA, it was SOM, excuse me. So he was at SOM, in Chicago in 1977. So this was when almost no architecture offices had computers. So you had to be a really huge architecture office to be able to afford one, and so SOM did. And this guy, left SOM, left architecture, moved to California, and then started. So he's actually one of the founders of Wavefront, which later led to Maya. And so it's funny because he became one of the people who was in charge of creating the visual effects for Tron. So he was really like a visual effects person who had architecture training or was an architect originally, but then funny enough, his software later became really important in architecture again. So there's kind of like a closed loop here where it went through the movie industry, just like NURBS were not really invented for architects. They were invented for other and adapted for the shipbuilding industry. Meshes were actually adapted from the movie industry. And so here's just some early examples of how meshes were used in animation. I mean, and at the time, each second of these movies cost like millions of dollars because it took so much computing power, and computers were so expensive. But now meshes are used everywhere. Like, I mean, even in like TV show, it doesn't have to be even a movie, but like it's really like very, very mainstream. Even in places where you maybe wouldn't expect. So even South Park, which is a very flat cartoon, if you see a screenshot of it's actually being animated in Maya. But movies kind of in a way are in some sense the origin, but now meshes are applied for or used in all kinds of industry, in flow simulation, where people are trying to describe sort of wind flows on aerodynamic shapes, or in design. I mean, the low poly look is has been popular, and it kind of keeps coming back in waves of being kind of popular, being used in art. Here it's used to recreate a full-scale cave, which is really awesome. This is like at the Prada Foundation in Milan, where they recreated an entire cave and 3D printed it, and this is kind of like related to what we're doing, where it's sort of like looking at reality and sort of trying to recreate it. And finally, how did they get to architecture? So essentially, in the late 90s, early 2000s, people like Greg Lynn were sort of early pioneers of using meshes in architecture, and they were very interested in the ability of meshes to be animated and to change. And so here you can see the embryological house. I'm just curious, have you guys heard of the embryological house before? No? Okay, so the idea behind the embryological house was that it doesn't have a fixed shape, but it's constantly changing. And here you can see sort of like various iteration of that same house, kind of like almost like stop frames of an animation, but they were sort of thinking that architecture is actually gonna become this sort of organic shape that keeps changing. And here Hernan Diaz Alonso is also like a proponent of that early, I would say, exuberance of meshes, where people, and you can really tell that this is like a subdivision shape that's been sort of just pushed and pulled, and there are holes put into it and so on. And these people were not necessarily interested in building; they were just interested in the technology and how far you could push the technology into creating a new world. And Hernan Diaz Alonso is now the dean at SCIARC, which is a school that's very, very focused on digital work and digital, in a way, avant-garde. So there is a whole discourse of architecture, I would say, that's dedicated to this type of work, and obviously it's been taken much further. I mean, this is like an early example of him doing that. I mean, now this is very much also going into video games, into VR, and so on. But it's kind of like the beginnings of it. One way, this is a project I worked on in school back in Vienna. So I mentioned how sort of the tessellation patterns or the kind of like subdivision patterns can be used for design. So here we're trying to kind of exploit that and working with like overlaying different patterns. So in 3D Max, using one pattern and then another one on top of it to create these different shapes and different patterns. And so here's like a physical installation out of panels that we built from that. And here's another architect that has been using meshes profusely, which is Mark Gage. He is a New York-based architect who's also teaching at Yale, and he invented this, or I don't know if he invented, but definitely wrote about and theorized this idea of kit bashing, where you take a lot of sort of ready-made elements from the web. So if you download models from TurboSquid or whatever service you're using, or SketchUp, all these models are meshes, and so you can use these presets and then just smash them together and create like new ornaments or new geometries. And this is some example of like this sort of fantasy buildings that he created that are kind of combined from existing content. And kind of like I was talking about, build examples of the Rhino, where you can sort of see Rhino being built. You can also now see the meshes or 3D Max or Maya being built in physical form. So as similar to the architecture, they were using Maya very heavily. I used to work there a long time ago, and it was these projects, they're very formally, clearly originating from sort of mesh sculpting capabilities. And MAD, again, this shape is a subdivision form. And then, maybe one of the most famous proponents of that style is Zaha Hadid, which is very interesting because she, in a way, already made these drawings way before. There's basically like a pre-digital Zaha and then a kind of like post-digital Zaha. And the two are related, but they're not quite the same. You can definitely see how the digital tools changed and kind of influenced her style after she started using them. So, she had already a very dynamic style, and I think the tools were like in line with what she was thinking, but there is this sort of subdivision quality to her buildings. Yeah, here's just some more examples of this like very organic sort of structures that have been built. And to finish with this project by Zaha, where, you know, to me, it's kind of fascinating as an idea that polygons were invented to describe reality, but then in the end, they also became a design tool. So now they're back into being built reality in physical space. So sort of these tools have been subverted by architects and are being used in that way. And you know, even just the distillation pattern is something that, you know, kind of comes out of the software and the way that the software is being used. And yeah, I think now, you know, this is like kind of early 2000s work. I think we're kind of entering a new phase of let's say digital experimentation, which is maybe a little bit less interested in creating this smooth formal shapes. I mean, which is totally fair, and people still do that, but I think where meshes have become incredibly powerful and interested in, to me personally, I guess, and also in this class, is, you know, in the areas of sort of 3D scanning and WebVR and you know, exactly what we're doing here, the idea that you can just like scan anything, represent reality and use it for your project as like, you know, either like as a resource to document the site, or as a way to share your 3D model with somebody else, as a way to, you know, if you understand meshes and how they work, you can optimize your Rhino model and then you know, turn it into a mesh and then drop it into an AR app or a VR app to actually experience it in the physical space. So this is kind of like where it's going for me with meshes, you know, so like a little bit maybe back to the original purpose in terms of like thinking about how meshes are used to represent reality, and kind of like, but now really being able to mix with reality, especially with AR. And that's it. That's the my lecture. How are you guys feeling? So has that changed your definition or thoughts a little bit? Would you describe meshes versus NURBS a little differently?
I definitely understand them better now.
Yeah. Yeah, I think it was interesting to see how obvious it was in some examples, what software people were using to create building.
Yeah, I mean, it's definitely strange once you know how it's made, you know, you can totally read it.
I mean, something even as simple as building originally a mass in NURBS, and then converting it to mesh, and then back and forth until it's some combination. It's something I'm interested in. I've tried before.
Wait, to convert it into a mesh and go back and forth?
Yeah. Yes. So that it originally it's like a waveform from NURBS, and then you almost panelize it using by converting it to a mesh.
Right.
And then reforming it by lofting it as NURBS, and then meshing it again.
Definitely. I mean, I didn't talk so much about the exchange between it, but obviously it can also be used, you know, there's lots of like interchange between two import ways of exporting and importing. But there's still, I think it's important to understand that like each of these softwares is sort of rooted in one of these. I mean, you can open NURBS in 3D Max and you can open meshes in Rhino, but they're just often not going to work the way you think because this software isn't originally designed for that. So, yeah. Oh, there's a puppy. Yeah. I mean,
I think the new Rhino 7 that is coming out, I think is this year, they actually they're promoting this sub D on NURBS, which you resurface, and then it kind of gives you like how many, I guess, curves you want to like adjust it. So now with the sub D, you can actually take one of the panels and completely just work on that instead of working an entire geometry itself. So I guess maybe in the future they are trying to combine what Dan is pretty much saying, that, like you said, Rhino is not like a program that reads the meshes that well. But then at some point in the future, the NURBS are going to be read as a mesh, and it's going to be work better. And also, from what I know, I think meshes are mostly used for rendering, right? They're like they are read better than the NURBS itself.
Actually, you can't render NURBS. Every NURBS is going to be meshed before rendering. So, yeah, so meshes are definitely better for rendering. Yeah.
I always thought that maybe in real time it created surfaces on a series of curves and points in NURBS, and then the surfaces themselves and the poly surfaces were just a 3D representation built in real time for us to be able to visualize it. But in the background, it's actually just curves and points.
I mean, honestly, I'm not a super expert in how exactly render processes work in terms of how you know the geometry literally gets translated to be rendered, but I do. Yeah, I mean, you could just very generally say. I mean, it's gotten, and you guys are totally right. Like in a way, these differences are collapsing more and more. But that's why I think it's important to still know about them so you can understand how they have collapsed or how they have sort of merged. Rhino is getting better and having meshes, and actually I use V-Ray for Rhino all the time because we do model mostly in Rhino at this point. It's more precise, it's easier, and so on. So it's easier to produce plans in 3D Max. It's very hard to actually produce plans, but for a long time people would like model in Rhino and then they would export to 3D Max because it was so much better for rendering. So yeah, I think these technologies are going to come together, but in a way, I think these fundamental differences will probably stay in place. And actually, it's funny you mentioned that Rhino is starting to do sub-D. I mean, actually, they've had a very similar thing a few years ago, where maybe like it was probably like Rhino 4, where they started some kind of like sub-D Rhino thing, and it totally failed. And maybe this time it will be better. We'll see. It's just hard to create that type of efficiency as with meshes. I mean, I know you guys are kind of fighting with like big mesh sizes because you're not starting with like a low poly model and building up complexity from that, which is sort of like which is really like the correct way to work with meshes, right? Like we're hacking the whole system, we're creating scans, and then sort of like doing almost like the opposite. We're like reducing the number of polygons from these scans to create manageable meshes and in order to be able to edit them. So it's a bit of a backward way of working almost, but it doesn't matter. It's still a way of understanding, these meshes, and I think actually a really good way of understanding what meshes originally were meant for. And I think if you're interested in it, you can go deeper and start learning more about actually how to create meshes from scratch. I mean, some of you already have, but like, I think that's definitely a very useful skill as well. And I think architecture, in general, has been like very, very focused on NURBS in the past years. But I do think that both of them are important, and we should just know of both and know when to use which one and so on. Yeah.
I was also wondering, I didn't know that there were different kinds of meshes. I was only familiar with triangulated. I didn't realize that there was quad panel meshes and hexagonal meshes.
Yeah.
I wish that there were tools to be more transparent, even in like Mudbox and Mesh Mixer, to view your model as if it was a different kind of mesh.
Yeah, I think, those things do exist. They're just pretty computing heavy, and generally most modelers work with quad meshes. There's some triangular meshes, but quads is like really the most common one. And I'm not sure actually why not triangles. It seems like, yeah, but quads is really the default. But there are algorithms that will take a quad mesh and turn it into like a hexagon mesh, for example. Yeah. Cool. All right, I'll put that lecture online as well, so you can refer back to it. I'll send you guys the Baumgart essay. And again, apologies. You know, crazy times. But so I'll see a lot of you for desk grids tomorrow. And the one thing that that got cut short is discussion of the reading. So I'm wondering if maybe we can, maybe we can do like a voluntary, whoever wants to discuss it, and just add it onto the timeline tomorrow after desk grid. So whoever was around and wants to talk about the reading, because I do think it's a really good one. So I think now we have people signed up. Oh, so Joel, you signed up for today. Are you free tomorrow? You're the only person that, can you do tomorrow at 4:20? Because then we could just do like you know, sort of a little bit more loose discussion of whoever wants to do it from 5 to 6. And I understand if you guys have other things, but because that's like the one thing that we didn't really have time for today. That's the ones to do.
Professor, I was just having a little trouble to upload my stuff on the poly because the file is too, bless you. And I don't know how to reduce the OBJ.
I was having the same problem, Joel, so thank you for asking.
Yeah, it's just like I was doing all my sculpting in Modbox, that's what it's called. And then when I was like trying to put it online, it was too big, extremely big.
You could just go in the drop down that says mesh at the top left, and then do reduce mesh.
And you're saying that's done in Modbox, Dan?